Okay, let's begin. So today I was going to... I know that I did a little bit of a lecture last time on binary search trees on Friday. I did BSTs, and I was basically trying to recover some of the lost lectures from the snow day and the early Comcast problems in the semester. So, but I feel like probably what's going to end up happening is that most people are going to either watch that lecture late, or maybe some of you haven't seen it yet. So I'm going to review quickly some ideas, how to find, insert, etc. I've already done the live coding for it, so if you want to see that, go to the other lecture. I'm not going to repeat everything, but I will probably redo some of the coding in a different way. And I see that we have the true loyalists here today. Everyone else is probably panicking, working on their projects. I will be, I guess the other thing to say is I will be releasing Homework 2, probably today or tomorrow. Sometime tonight, maybe. It'll be due next Thursday. The other thing to say is that Project 2 is going to come out, and I'll go over that Thursday. So it's always unfortunate, right? It's terrible that this lecture is today, because it means that people are working on their projects. I'm not entirely sure what the answer to that is. I mean, I guess I could always just reschedule the lecture to a different day, but then that would be unfair. There's a lot of theoretical ways that I could solve this problem, but I don't think there's any 100% perfect solution to any of it. Okay, so in terms of the projects, I will be available after class, and I'll be around. I'm not going to promise that I'm going to be like fully sitting on my computer until 9 o'clock, but I'll be available after class to help with any I'll call them last minute emergency bugs, right? And I know that one or two people have already asked me for help, so I'll help them after class, and then we can basically form a queue in the general channel in Discord. So that's that. I'll be around to get all of you through if I can. Can't promise that. It's funny because I actually did. I hadn't coded the project until recently, and I did code the project, so I have some idea of how it should work, and I have some idea of basically the bugs that you might run into. But I can't always promise that I'll find every bug, because some of the stuff in C++ is just very, 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 very subtle. But anyway, we will make our best attempt to find all the bugs and to do all of that stuff. So, okay, so that's all I really have in terms of announcements. I guess what I'll say is that the exam will be given maybe starting next Thursday, and you'll have over spring break, and it'll be due maybe the Thursday when we come back. So you'll have basically something on the order of like 2 weeks to work on it. That's an exception. Normally I'm only going to give you 1 week, but I'm not going to make anything due over spring break, so nothing due over spring break. So that's why we're doing it. Most of the other exam, the second midterm, and the final, they'll both just be 1 week only. Okay, so that's that. Because spring break is coming up, I think, right? It's not next week, but it's the week after that. And I know that probably no one is doing anything for spring break, because what would you even do? But I don't know. Maybe you're gonna have a lot of fun and go out to a beach that I don't know. But anyway, the point is that okay, that's I think currently what I'm thinking. I'll write the exam for next Thursday. So we'll have 2 homeworks, and then the exam. Then we'll have 2 more homeworks, and then the second midterm, and then 2 more homeworks, and then the final. And that's how it'll work. So we'll have 2 homeworks between exams. 2 times homeworks between exams. Okay. Okay, so yeah, so that's enough in terms of announcements. Let's get back to actually looking at the binary search tree nonsense, right? So what is a binary search tree? What is a binary search tree? Right, so basically the term binary tree means a tree, and of course I should say, what is a tree? It's a graph, meaning circles and lines connecting, right? That's our current definition of a graph, that has no cycles, okay? No cycles. So that's what a tree is. It's an acyclic graph. Sometimes people even put the term directed, meaning that there's arrows on the lines, but you can take the arrows on and off. The point is that a tree is a graph. It's dots and like circles. What do I mean by circles? Like basically what I mean is it's vertices slash nodes, right? Whatever you want to call them, and edges. And the edges do not ever go in a circle. So there's no path that. I guess what I mean by no edges, so no cycles, is something like this, right? So you never have anything where you would start at one node and then be able to take a path around, right? It doesn't end up going back by the same path. So you can take a path here where you never have to travel the same edge again, right, to get back to the same node. So you can get back to this node by going around this way, or you can go around this way. So this is a cyclic graph. This is also a cyclic graph, like if you do this kind of stuff and you connect this one, and then you can even do crazier stuff and just directly connect like these two edges and all that stuff. So this is a really cyclic graph. But all you needed was that one cycle to make it a graph. So a cyclic graph, I mean. So a binary search tree is something that has no cycles, right? And what does the term binary mean? Binary means each node has at most 2 children popping out of it. It can be 0, can be 1. If it couldn't be 0, then you would have an infinite tree, which we don't really talk about in computer science just because, I mean, infinite trees exist in mathematics, but we don't really talk about them in computer science just because you can't actually model them on a computer. And the search property just means that as you search down this tree, right? And let's draw an example of such a tree. So let's say here's an example of a binary search tree. Let's see if I can do justice to it really quickly. And then here we are. And then let's just draw in some lines. Oops. There we go. So there we go. So now we have some lines. And so here's an example of a binary search tree. What it means is that if there's values in the nodes, so the nodes have values. Let's say that this node's value is 15. I hate that it's snapping there, but whatever. Let's make this node's value 8, 3, 12. Let's make this 17, 16, and 22. So the point about these, and I do apologize that they're all kind of nasty looking. There we go. I can kind of fix it, at least vertically. It's harder to fix it horizontally. So the point is that how do you find a node, right? Given a value to search for, how do you find it? And the answer is, if it's less, go left. If it's greater than or equal, go right. And that's literally it. That's what the search property means. It just means that this tree is, and the thing is, we're not going to see a lot of like binary trees that aren't search trees. So sometimes you'll even hear me just say binary search tree, and I won't even realize it if I've said like search when I don't mean it, because the thing is that these things are usually the standard thing that you do with a binary tree, and the reason for that is because let's say I'm searching for the number 12 here, so 12 is less than 15, so I go left, right, and then 12 is bigger than 8, so I go right. And that's it. And then I find it. If I'm searching for 13, for instance, right, I say 13 is less than 15, so go left. 13 is bigger than 8, so go right. 13 is bigger than 12, so go right. And then what do you see here? Right, what we see is that the nodes at the bottom of the tree, right, because we continue the tree analogy, we call them leaves. We call the thing at the top of the tree the root, right? And then what are the things at the very bottom here? These things are just null pointers. So you might be able to call that a leaf, and sometimes there are some books that actually call null pointers leaves. I tend to prefer to call a real node, a node that exists with an actual piece of data in it, a leaf, at least until I say otherwise. So leaves are the bottom actual nodes. If we get down to a null pointer, then I'm just saying that we're like off the tree, right? Like this edge doesn't really exist because it just points to a null pointer instead of pointing to a node. So basically that's right. So now we know what a binary thing is, and so let's draw out a binary search tree that isn't so perfect, right? So what you can do here is you can just say, well, is this still a binary search tree, right? And let's delete this, put this here, and make this say, well, now this is not a binary search tree anymore because it doesn't satisfy the search tree property because 3 is in the wrong place. But now, if you look here, does this satisfy the binary search tree property? Is this a binary search tree? So this one's a leaf, this one's a leaf, this one's a leaf. And let's even add another node here. Let's make, I guess the only thing that can actually go in here is 16 because it has to be bigger than or equal to 16 but less than 17. So it can only be 16. So as it turns out, this is still a binary search tree, right? Even if you only have one node as a child. So for instance here, if I add a node, say 1 here, you might say, well, is this a binary search tree anymore? Because this node only has one child on the left and it has a null pointer on the right. The answer is this is still a binary search tree, okay? Still a binary search tree. Okay. So, just as a bit of a review, let me go over the code that I used to code up the binary search tree. So let me look at all the stuff. So let's go to the node class just to start there. Where is it? Oh, it's probably in the .h file. Here it is. So I made a thing called a tree node. And it has a left pointer, it has a right pointer, and it just has a thing called data, right? Which in our case, because I'm just teaching the data structure, is just an int. But really, this can be anything as long as it's comparable, right? Which means that it needs to have like a less than sign, maybe an equal sign. It needs to have at least these two operators, and they need to work as you would expect. Like for instance, they need to have, what should I say? They need to have properties like transitivity. So for instance, if A is less than B and B is less than C, then A has to be less than C. Otherwise, you end up with real issues. So if you can invent a less than operator, like you just like overload, right? And other thingy, right? And then you, just do some garbage, return garbage. It's not necessarily just good enough to be something that you can make into a binary search tree. It actually has to satisfy the properties of being an operator. Or I shouldn't say an operator. It has to satisfy the property of being, what do we call it? A partial order at least, right? On the set of data elements. Probably a full order, really. But that's all mathematical nonsense. So anyway, here what we have is we have the tree node, we have the data, we have the destructor, which we can ignore for now, but we'll pay attention to it in just a second. And then That's it. That's really it. So basically, this is like a linked list node, right? Except instead of having one pointer, and of course you might say, well, a doubly linked list has 2 pointers. Point valid. But instead of having just one pointer called like m next or whatever, you basically here you have like m left or p left or whatever. You have, p left and p right. Right? And so that's the way that you make the tree, because now you have 2 directions with 2 directions to go in. Of course, anyway. All right. So I wrote one way to do the find operation. And I think in order to write delete, we're going to have to do another find operation. We're going to have to do a find node. So let's make a tree node pointer find node. And then let's just do int data. And then we'll also need a tree node pointer get successor to a tree node pointer p current. So we'll need these 2 functions to actually do the remove function, but I'd like to use the find node as an opportunity to recode the so remember how find worked, right? Find worked just as a while loop here, and I think this is actually probably the better solution because it doesn't involve recursion, but I would like to show you the recursive version of this process just so that you have a good idea of how to do it. If you're ever thinking, well, do I need to do the while loop or can I do recursion? The answer is you can do either one, and let me show you. So here, if you're looking for a node, you go while the current node is not equal to null pointer. If it's ever equal to null pointer, then that means that we have the data is actually not in the tree. We reached a null pointer before we found the data. So if data is less than the pcurrent.data, this is the thing where it says go left. Else if it's bigger than, you go right. And else basically, if it's not less and not greater than, it should be equal. So you return true, right? So you found the thing, right? So this is like a Boolean find. Have you found the data in the structure, right? So let me show you the recursive version of this thing. And let's see how we can make the recursive version work. So we're actually going to need a recursive helper function for it. So let's just do find node rec. We'll call it find node rec for find node recursive helper. I hate using the term helper actually in a function name, but that's just a personal preference. So what we're going to do is just return the find node on data and is it mroot? Yes, I called it mroot. And so here what we're going to have to do is we're actually going to have to make this tree node pointer p current. Right? And this is all we need to do here is just find the node from the root. Let's actually put this function into our class so that it doesn't keep yelling at us, because it really wants to yell at us. Okay. All right, so here we are. And now what's the problem here? Too many arguments. Expected single argument data. Oh, because I didn't use that. Okay. All right. So now how do you? So this is just like the public. Well, it's not even public. This is the private function that does it. But this is the function you would actually call. This is the function that is going to do all the work, right? So basically here, what we're going to do is we're going to say if not pcurrent, meaning if pcurrent is a null pointer, and it's okay if you, the other alternative, and I see a lot of people doing this, you can just say if pcurrent is not equal to null pointer or is equal to null pointer, that kind of thing. I see a lot of people doing that. I'm back from, this is kind of like the old school way of doing it, where you just evaluate if the pointer is false, meaning it's 0, then it's and null pointer always evaluates to false. So there we go. Okay. So if not pcurrent, we'll just return a null pointer. And the reason why we're going to do that is because if pcurrent is false, that means that at some point we've fallen through the tree and we haven't found the thing already, right? So this means we've gone through the tree, haven't found the thing. Okay, so what do we do now? So now we can assume that pcurrent is true, and so you can either use an else here or just not. It's up to you, right? I think it probably all compiles out the same way, so you don't really have to be exceptionally concerned about it. I don't think there's like a significant improvement to the efficiency to do it one way or the other. But anyway, so if pcurrent, let's say if data is less than pcurrent dot data, then what we're going to do is we're going to return find node rec data pcurrent dot left, right? And so this is basically the same thing as going left, except now we're just returning it. And then what we do is we say, I guess actually what we could do is we could always check first. If data is equal to pcurrent dot data, return pcurrent, right? There we go. And then we do else if this, and then we can just do else p_right. Right, so the else means that it's not equal and it's not less than, so it has to be greater than. Right? Not equal, not less than means greater than. And of course, this is why when we require basically this is why we require the operator, this less than operator, to work correctly, because here the thing is that it needs to be, if it's bigger, if it's not less than and not equal to, it has to be greater than. But technically, you can overload this operator to do whatever you want if you have some other class there. So you always have to be slightly careful, maybe a little bit concerned about, as long as that operator works correctly. Okay. So anyway, this is like the recursive version of find, right? So instead of coding up find like this, what we could really do here is we could just say find node recursively data mroot, and then return this is not equal to null pointer, right? So basically, this is an alternative way to code find up. Okay, so that's an alternative way to code find. And it all just would use the find node recursively function. The only reason why the recursive stuff is good is because it allows you to always just have like one node that you're currently dealing with here, and you're never actually reassigning it, right? So in the next version of the function, pcurrent is just the next node down. And so that simplifies your life a little bit. The only thing that it does do is it actually, puts a new function call on the stack. So remember that basically there is a piece of memory in every program called the recursion stack or the call stack. And every time you make a function call, it does use up a little bit of RAM to do it. So if you're going to have like 1 million recursive calls, most likely your program is going to run out of that stack space, because that stack space isn't as big. It's not as big as your total memory space for the program, because for your program you have code space, you have the stack space, and you have the heap space. And the heap space is for all the dynamic stuff, and the stack space is for all the static stuff, including all the variables, all function calls, everything like that. And so you can easily, well, I shouldn't say easily, you can run out if you end up doing something like 1 million function calls. So, I mean, but it's good to know how to do both things, so I think that's important. Okay. All right. So now let's talk about, so we talked about insert last time, and let me just quickly go over how insert works. Where is insert here? So insert is a lot like find, right? Basically, what we're going to do, we have an edge case here, if the root doesn't exist, then we create a new root with we create a new tree node root with the right data. Okay, that's it. So what if the root isn't null, right? What if it isn't null? Then we do this. And you notice it's almost the same thing as find, where if the data is less than the pcurrent.data, you set... So I'm doing parent here, and you'll see why I'm using the parent in just a second. So parent is equal to current, current is equal to current.pleft. And so we're just going left, but keeping track of the parent. Here we're going right, but keeping track of the parent. And then here, if the data is less than the parent.data, we put it as the left child. And if it's else, we put it as the right child. So this is a decent insert algorithm. There's a lot of different ways to do it that are kind of variations on a theme. So it's always possible to do a different insert algorithm that's slightly different. Like, for instance, you can move these if statements up into these two blocks here and have them nested. And it changes the code a little bit. You don't have to keep track of the parent anymore. And you can change the condition of the while loop. But there's a lot of different ways to do this stuff. So this is one way. Okay, and then I wrote this display subtree method, which took me a while to get working correctly because of all the tab stops and random stuff. So I just made these spaces. It's actually pretty disgusting looking, but it does work now. Okay, so... Alright, so I wanted to talk now about... So basically, the previous lecture, so if you're still confused about insert, go back and watch the previous lecture where I implement insert, right? I'm not going to re-implement insert recursively, but you can do it, but you don't, it can also be done recursively. Now I want to talk about remove. So remove where we remove by data, right? So we search for something and we remove it. So basically, what are the steps to remove? The steps to remove are, first, you find the node, which is exactly why I wrote that little helper function. And then remember what you have to do. So we have to find the successor. So I'll call this del node equals this. And then we have to find the successor, or get successor, of the delete node. And of course, you might be asking, what is the successor? So the successor of a node is the least node in the right subtree of the node, under that node. So for instance here, the successor of 15 in this case is the least node in the right subtree. So it's you go to the right subtree 17, and then you track left as far as you can, so 16. For instance here, the successor of this node is the least node in the right subtree, so least node in the right subtree, you go right by 1, and then you go left as far as possible. And so here the thing is that if we had, let's add another level to this binary search tree. Let's put, for instance, a node here. We could even put a 9 here, I think. And then we could even do something else. We could put like an 8 here. And here we go. So we can do this because, and if you notice, this is not under any of these nodes. This is actually part of this subtree here. So the successor of 8 here is actually, well, let's just pretend we can use decimal numbers. So this is 8.1, right? So the successor of 8 here is 8.1. Or if you pretend that you can only use ints, then it's just 8, but it's the same value, whatever. So basically, to find the successor, right, you go right, and then you go, and then you do that one time, and then you go left as many times as you can, right? So that's what you do. and then that node is the successor. Okay, and now why do we want to look for the successor? And I think I went through it last time about why we can't just... The problem is, like in a linked list, you can just pull out a node and then just relink it. But here, the problem is if you pull out this node, you have these two connections that you have to deal with. So it's not as simple as just saying, oh, I'll just connect this one up to here, or I'll just connect this one up to here. What you would have to do is then you would have to promote, say, this node up to here, and then you would have to attach this node as the right child. But then what if this node already had a right child, right? So like what if the number 5 was sitting in here? Then you couldn't attach it there, so you'd have to like keep looking for a place to attach it. And that's the problem with remove. If you just tried to like pull out a node from the middle of a tree. So the answer is we avoid doing that. We never extract a node from the middle of a tree. We only kill off a leaf. And the reason why we only kill off a leaf is that leaves have no children, right? So we know that if we delete a leaf, so once we delete this 8.1, it doesn't have any children, so we know there won't be any problems, right? Whereas if we deleted, say, 8 here, or 17 here, or 16 here, or 12 here, the problem is if we just deleted these nodes, we would have to, you have to like physically, as a human being, like look through the tree and saying, oh, well, it kind of makes sense to maybe connect the 10 up here, and then you connect the 12 down here, or maybe you do it the other way, you connect the 12 up here, and then you connect the 10 as the left child, right? You can do both things. Of course, it makes a slightly bigger tree if you do it the second way. But that, I mean, you know, that doesn't really matter. So the whole point here is that, so the point here is that, you know, because we have more than one branch coming off, it just gives us a little bit of extra difficulty. And so that's why we find the successor. So we find the successor, and then what we do, and then here's how we continue to delete. We copy the value from the successor up into the node itself, right? So, and then what we can do is delete the leaf, right? So copy value from successor to delete node, and then delete the successor, right? Not the delete node, right? So delete node is the thing where we're trying to delete the value, but the successor is the actual node that pays the price, right? This node no longer is necessary because we've copied its value up. The 8 that was here is gone, so the value in this node is gone, but then this node gets to go away, and this node is a leaf. And there's actually an edge case to this that I talked about last time, I haven't talked about yet. But before we do that, let's code up the successor algorithm. So let's code it up iteratively, because I think that's usually the easiest way to do it. So where is it? So get successor. So we're going to assume pCurrent is not null, but let's check it, right? If pCurrent, else we're just going to return like null pointer, right? Be like not a human. You tried to get the successor of a null node. Technically, you could even throw an exception, but I'm not going to do that because I'm not going to catch that exception, and so it would just cause crashes, right? So if you don't catch uncaught exceptions, will eventually terminate your program. So okay, how do you get a successor, right? You get a successor by going right once. So go right once. So pCurrent, successor equals, let's just do auto successor equals pCurrent dot p right. And so remember what auto does. Auto is the lazy way of saying to C++, you know what type it is, okay? And so it just automatically determines what type it is. pCurrent.pWrite is a tree node pointer, so this thing is a tree node pointer, right? You have to be a little bit careful with auto, but I was just too lazy. I like had a brain fart and just forgot what type it was for like 0.2 of a second, so I just used auto instead. It also kind of looks more modern, a bit more modern. And then, so what happens if, say if not successor, right? So what that means is that, So yeah, if the successor is false, then what does that mean? That means that there was not a right child. So in that case, we're actually, there's a little bit of a edge case, but we can just return null pointer here. What I mean is there's an edge case in delete, so we can just return null pointer. So now we get to assume that there is a successor. At this point, there is a successor, meaning there's one node on the right. And so now what we're going to do is we're just going to go left, right? So while successor dot p left, right? Successor equals successor dot. And I always use dot for both arrow and dot p left, right? And so then here we can just return successor. And that's it. That's really it. So this is basically the code. These, 3 lines plus the return statement. So for these 4 lines, this is just checking for an edge case where someone tries to, so the thing is, like, if you try to delete a leaf, you're going to get that there isn't a successor. If there's no successor, for instance, if I actually just tried to delete a leaf here, so if I tried to delete 16, this 16 here, for instance, I wouldn't have to worry about it. I could just delete it, right? Its successor is null. There's nothing to put up in its position, so you just kill off the node. Now you might ask, what if there's a left child here, and that's an edge case that we'll have to deal with. But, yes. So there is an edge case here that we haven't talked about, which is where it has a left child. The successor, I'm sorry, the successor can't have a left child, but the successor can have a right child. Like this successor has a right. If we were trying to delete 17, you would note here that the successor here actually has a right child, so it's a little, so we would copy this data element up, but then we would also have to delete this node. So there's a little bit of a recursive thing that goes on. Anyway, so, okay. All right, so I think that's basically it for finding successor, right? I mean, we've done it because we've gone right once, and then we go left as far as we can, and, you know, while the successor dot p left. And so my hope is that I haven't gone too far. I think this is right where it won't go too far. Okay. Okay. So let's code up delete. At least some of the parts of delete. So why are you unhappy? Function is never used. Well, we're about to use it. But don't worry. So, yeah. So where is remove? Here it is. So remember the steps. The first step is you find the node. So you'll do, you know what, I'm even too lazy. Let's just do auto, which is, I'll just tree node pointer. Tree node pointer, find node, data. Okay, wonderful. I'll call this del node because that's what I was calling it before. And then we'll do a get successor. Now you can do this all in one function, but I like to kind of split them up into little helper functions just because I find it easier to test. Right? Crap, I've lost myself. Here we are. Tree node pointer, successor equals this. And so now assuming that the successor doesn't have a right child, so let's just say if successor, right? So if the successor doesn't have a right child, then, or if the successor doesn't exist, I guess there's actually a more fundamental thing to do. So first, if the delete node doesn't exist, meaning we couldn't find it, then we should just return, right, immediately. Or throw an exception or something, because the point is, like, you tried to remove something that wasn't in the tree, right? Tried to remove something not in the tree. And you might say, well, that's not exactly part of our steps, but, you know, it's definitely an edge case that we have to think about when we're actually doing the coding of it. Okay, so cool. Now we assume that the delete node, we at least found the node, right? If we haven't found the node, we're out. Here's the successor. So if the successor doesn't exist, then basically what we can do is interesting. Then we actually have to delete the delete node. So we need the parent of the node itself. So it might help to do this recursively, or it might help to just maybe have find node also return the parent or something. We'll have to think about it. So let's just do a tree node pointer parent and equals something, right? It's not equal to anything right now, but you know. So why do we need the parent? And the answer is because if we don't have the parent, then the parent dot left p left or the parent dot p right is going to be equal to the actual tree node is equal to the find node, right? Delete node. And so if it's the case, and then I guess really we'll have else here, right? So if it's either the left parent or the right, or I'm sorry, the left child or the right child of its parent, then the answer is we actually need to set. So first we need to do like a delete on del node, and then we need to do parent dot p left is equal to null pointer. And the reason is because if you don't do that, then it's not going to know, right? It doesn't know that child was killed. So so let's do p right here. And of course you might say, well, why don't we just delete the node up here before the if statement? That way we don't have to do it twice. I agree. What's the problem here? If identical, then else print. I think that's only because it doesn't understand what parent is that it's yelling at me. So we need to make sure that we get the parent somehow. Now there's two, and I'll describe how we can actually resolve this problem. So there's like a few ways to resolve this issue, right? Because you're asking yourself, how do I get the parent of a node? Yeah, we'll try to resolve it. So okay. Okay, cool. So here's if the successor doesn't exist, then basically what we have to do is say if the parent.p left is equal to the delete node, then we kill them off, and that's it. That's it. So now that's another edge case that we haven't dealt with. So what if the successor does exist, right? What if the successor does exist? So we find the node, the successor exists, right? So what we're going to have to do is we need to delete the node, or we need to transfer the value. Right now we're at step 3, which is copy the value from the successor to the delete node, right? So how do we do that? So what we're going to have to do is, so what we have to do there is just say that the del node dot data is equal to the successor dot data. Not complex, not terribly hard. Okay, so now that we've done that, now what do we do? So basically, if the successor is childless, right? If the successor is a leaf, so what we do is we say if successor p left or successor dot p right, then we have more to do, right? It's not a leaf. But if it is a leaf, right, then we can just delete it. So then we just say delete successor. But of course we need successor's parent too, so that we can tell it to, right, to forget about it. So we need to tell successor's parent to forget about it. Okay? So I guess we should resolve the parenting issue, because at this point I think that's kind of important, because we have two things with parents that we don't really have access to. So what should I do? I think one way of resolving the parent issue, and this is like the most common way to do it, is whenever you do a deletion operator, you just throw a parent in. And we'll set this parent to null pointer. Like that. And then what you do is you go back to the binary search tree, and then unfortunately we have to recode everything, right? Or I guess we don't have to recode everything. We just have to recode insert. And maybe we have to recode find as well, a little bit. So what do we do here to fix this? Well, pcurrent is equal to pcurrent.left, blah, blah, blah. Here we're going to insert. So here we do parent.pleft is equal to the new tree node. And then here we're just going to have to do parent.pleft.pparent equals parent. And here we're going to have to do the same thing with pwrite. So I think that's sufficient. That's sufficient to code up parents. So now we don't actually have to do any finding of the parent, because the good news is that the del node is going to have a parent object. Okay? And we don't consider this as a third branch of the tree, because the thing is that technically this is a third pointer inside of the node, but we only consider the left and the right nodes as the actual edges. We consider this parent pointer as just a cheating little way to go back in the graph. So it doesn't break the fact that it's a tree. It just allows us to go up and down and find the parent. So, So here we have this, and we're setting that to null pointer because the tree node is, there's no successor. So we're just deleting the current node. And of course we still need to do that edge case there. And then here, so what we're going to do is we're going to say successor dot pparent dot pleft if, and so this is unfortunately what you have to do. You don't exactly remember which way you came from, so you're just going to have to check both ways. So if the successor is equal to the successor.parent.left, so basically saying if you are equal to your parent's left child, then we will forget about the parent's left child. So we'll say successor.pparent.pleft is equal to null pointer. And then else you are the right child, so we'll just do this with p right. So the good news is that we know that you have to be either the left child or the right child of the successor. Or really, I should say, the successor has to be either its parent's left or parent's right child. So there should be no other options. So hopefully this should satisfy our, satisfy us and be complete. It's always possible. Whenever you do multiple pointers like this, so let me just say this, multiple pointer arrows like this yield segfaults very easily, right? Because the most easy way that this would be a segfault is if successor dot pparent is null, and then we try to access pleft. So the thing is that the reason why this is the easiest way to get to a segfault is because we've already done the obvious thing. We've already checked, right? Here we know that the successor exists. We also know that the successor doesn't have a left or a right child, so in this case it's a leaf. But we don't know if the successor has a parent. I mean, of course we assume it does, because a successor is always a child at least, or it's some descendant of the node that we're actually trying to delete. So based on the structure of the tree, we know that's true. But if you have any bugs in your code, if you don't set parents correctly, all kinds of things can cause this term here. So this will probably not give you the segfault because you're probably going to check this. You're going to say, hey, wait, is successor equal to a null pointer, right? If it is, then I'm going to fix that. But is pparent equal to a null pointer? And that's the one that you always have to think about. So successor.pparent dot p left. So this is the operator here that will cause you trouble if anything does. Okay. So can we do this iteratively? I was going to do it recursively, but can we do it iteratively? Can we just do bool deleted was false, and then we say while not deleted, right? And so what we're going to do now is we are going to basically, well, no, we should probably just do it recursively. Yeah, we should probably just do that recursively. So instead of doing this iteratively, I think it makes the most sense to do it recursively. So what we're going to have to do is we're going to have to remove we'll have to have a remove node successor. And so that should take care of it. Basically what we're going to try to do is we will copy the node's value, right? Oh no, we've already done that. We've already copied the successor's data up into the node's data. And now we just have to remove this successor node. And technically, I guess we could just make this part of the check, but anyway. So okay, so this is basically what we have to do, and then let me show you what we're gonna have to, how we're gonna have to do this. So this is gonna have to be remove node. We'll change this to a tree node pointer remove del node or delete node. Call it that. And then instead of doing the find thing, so here we're gonna have to recode a new remove function. That actually just takes an int data. And then the first thing it's going to do is it's going to call this, and then we're just going to call remove node on the del node. And that's it. So let's add this to the binary search tree class as another helper function. Void. There we go. All right. Actually, we should just call it del node. There we go. Perfect. I think we fixed it. So, and you see why I have to do this, because I actually here, I need to remove a node, or a specific node. I can't remove a, you know, I can't remove it by value. I have to, because it's possible that there's multiple nodes with the same successor value, and we need to remove, well, I guess technically we don't need to remove this specific one, but I think it's probably best if you track down in the same path and remove the same node or that you're looking at. So there we are. So if the successor has a p left, well, the successor can't have a p left, right? So that's impossible. This is impossible. But it can have a p right. And so that's how we do it. Okay. So if the delete node is not in the tree, we do that. If the successor doesn't exist and the basically we have two cases here. So if the delete node has no children, right? So if it has a p right, that's impossible, right? Since it has no successor. But it's possible that it has a p left. And just having one one node as its child rather than two, there's actually a trick that we could do. We could actually just delete this current node and just relink it. So for instance, if we do like the del node dot p parent dot well, I guess we also don't know if the parent, so del node is equal to the parent's left, then what we can do is we can say del node dot p parent dot p left is equal to del node dot left. And then if it's the other child, we just do the same thing with the right. And then we can delete the node, and then it's gone. And then we forget about it. So doing deletion is a little bit, there's a lot of little edge cases that are necessary to check. And so there's one edge case that we haven't actually talked about yet, which is what if we're trying to remove the root, right? So if we're trying to remove the root, what happens? So here we need to check if del node is equal to m root, right? Because if it's equal to the m root, then the problem is that we actually don't have a p parent, so we can't do that. So we're gonna have to say that I guess here we'll just have to say that the m root is now equal to del node dot p left, and then we can delete. Now we can delete the del node here. And then what else can we do? The parent dot p left is equal to del node, so we would also have to prevent this from running. So we have to say if not parent, right? Then, or I guess we could actually just say if parent and then here we need else if parent. So that fixes that. So that's if that's the root. And then here we copy this up. So now we're not deleting the root because there is a successor. So we don't have to worry about it for the rest of it. But that is a concern here. If you're deleting the root, then you have to kind of never access the parent of the root, because the parent of the root is going to be a null pointer, right? So, yep. So that is delete. And that is pretty complicated, unfortunately. I think there's simpler ways to do this. Unfortunately, the problem is it's not infinitely simpler. I think that this way might be slightly longer, but it's not terribly longer. And it does cover all the edge cases. And so that's really the main issue here, is that, there's a bunch of edge cases that you have to cover, and they're all just adding a bunch of extra stuff to this. So the edge cases are, one, if you're the root. Two, if you don't have a successor, meaning no me.right. Three, if the successor is itself not a leaf, meaning that the successor dot right exists, right? And so those are basically the things that you have to worry about. So if you're the root, that's a problem. If you don't have a successor, that's a problem. If the successor itself is not a leaf, that's a problem. And we know how to solve all of these, right? If the successor isn't a leaf, then you just delete the successor node recursively. And then here, if you don't have a successor, then you have to basically delete the node and rejoin. And if you're the root, then you'll have to make sure that your mroot gets updated correctly. Otherwise, you lose your you can lose the entire tree, right? So those are the problems that you can face with delete, and it just I don't know if there's like a perfect way to code it very simply. I think it's unfortunately just something where you have to think about all these different cases. Okay, so let's do something a little bit easier as the last thing for today. So the last thing for today I think I'm going to do is we're going to talk about traversals. So there are 3 types of traversals of a tree. 3 types of traversals. Well, there's more than that, but really there's 3 that we're actually going to use. There's the pre-order, in-order, and post-order traversal. And in each case, let me just show you how these work. So the pre-order traversal, starting at a node, what you're going to do, and of course this is like pseudocode in a sense, but what you're going to do is you're going to pre-order traversal me.left, and you're going to output me. So output me. Then you're going to do a pre-order traversal on me.left and a pre-order traversal on me.right. And just realize these things are recursive. So, the first time I taught this class, I wasn't stressing enough, I think, that these functions are truly recursive, right? So, and I'll show you what I mean by that in just a second. So let's do a pre-order traversal. Let's look at, say, this tree here. Let's put it back into its original configuration and do a pre-order traversal of it. So let's move the 8.1 down to here. And then let's just do a pre-order traversal. So how do we do a pre-order traversal? We start at the root. So the root says output me, so we output the root. And then the root's left, so we have to do a pre-order traversal on 8. And then we have to do a pre-order traversal on 17. Right? So now we have to expand what pre-order traversal on 8 means. The pre-order traversal on 8 means that we're going to have 8 output because we output the node that we're at, and then we have to do a pre-order traversal on 3 and a pre-order traversal on 12, and we still have to do the one on 17, but we haven't gotten there yet. And then what we have to do is we have to do a pre-order traversal on 3, so we're going to do output 3. And then we do a pre-order traversal on 1, which, if you notice, is just going to output 1. It doesn't have any children, so it's done. So now the pre-order traversal on 12 is 12, and then p of 12. I'm sorry, p of 10, p of 12. Right? And then the pre-order traversal on 10 is, therefore, 10. Right? It outputs that node. And then pre-order traversal on 9. And then that happens one more time, right, where we get 9 times the pre-order, I don't know what I'm saying times, 9 pre-order traversal on 8, and then we still have the traversal on 12 and the traversal on, actually I should mark this is 12, let's call this 12 star, and let's call this 12 star, so that you know, and then we'll call this 16 star, so that you know it's the other 12 and the other 16. And then finally here, this is a pre-order traversal on 8.1, which just outputs 8.1. There's no children, so we're done. Okay, so now we do a pre-order traversal on 12, which outputs 12, and there's no children, so we're done. And then pre-order traversal on 17 means P17 times 16. And then finally here we get 16 pre-order traversal on 16 star. And then the pre-order traversal on 16 star, it just removes the... it just removes the P because there's nothing left to do. We just go down here and we're done. So this is a pre-order traversal, and you might be asking, how can I tell what's going on here? And the answer is this is always the root, right? So the first thing is the root. The second thing should be the left child, if it's less, right? If it's not less, then it's not the left child. But this is clearly the left child because it's less. This has to be the left child of this one because it's less. This one has to be the left child of this one because it's less. And so we can kind of reconstruct the tree a little bit. Anyway, so you see how here, this is basically going left, 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 and then the thing is that we can't go left anymore, can't go right, so we pop back up to here, and now we're at this 8 again, right? So actually we're here, and what we see is that we've gone through the left subtree, so now we have to go through the right subtree. And so here what you see is take 12, go left, take 10, go left, take 9, go left, take 8.1, go left, there's no left, go right, there's no right. So we're done. We return to this level, nothing right, so we're done. Return to this level, nothing right, so we're done. Return to this level. There is a right, so we output 12 star, and let me put the star on there because I added it. And so this is P of 12 star. And then there's no left or right, so we would pop back up. And then the point is here, anyway, so the point is that you cannot perfectly reconstruct the tree, but you can kind of take a guess at what's going on in the tree. There are ways to make a pre-order traversal where it is not possible to tell the actual structure of the tree. So, just by the way, now there is a way to actually do it, and the way to do it is to put parentheses around everything. If you put extra parentheses around everything, then you can tell. So, not technically possible to reconstruct the tree from this, but it is possible if you put parentheses. Okay, so what that means is that if we do something like this, where we say, put a parenthesis on everything that's in the right subtree, or I'm sorry, left subtree, and then we put a parenthesis on everything that's in the right subtree. And then we do the same thing again. So we say, okay, here we go. And then this one will have, I guess, this. So since there's only one thing here, it's possible to tell that this is the left child because it's less than this, and this is the right child because it's more than, or greater than or equal to. And then we do the same thing here, where we end here. And then this one also gets its own little paren, but there's nothing inside. And then, okay, so then we get a paren like this. And then we get this, 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 and then close, 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 close. Right, so this would be, I think, the output from a pre-order traversal with parentheses. And so it is possible to reconstruct the tree if you're given this data structure, because then you can exactly see how things are split. But if you're just given the listing, it's not technically possible. It is possible in certain cases, but there are cases in which it's possible to not be able to reconstruct a tree. And you can kind of imagine why that is, because the tree structure here has data that's kind of multi-dimensional, and here this is all just like a line, and so the thing is sometimes it's hard to tell if, for instance, a certain node is... Maybe I'll try to think of one to actually construct, but anyway. So let's talk about the in-order traversal now. So that's the pre-order traversal, right? So pre-order traversal does that. Let's talk about in-order traversal. The in-order traversal is the same as a pre-order traversal, except this is the difference, right? And now you can probably guess what a post-order traversal is. So a post-order traversal is the same as an in-order or pre-order traversal. The only difference is this, right? So now this is post-order. And this is post-order. So it does produce different looking data structures, right? So what about the in-order traversal? So the in-order traversal is going to go 15 first, or I'm sorry, not 15 first, obviously not. It's going to go left first, left first, left first. So it goes left, 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 right? That's what it tries to do. It tries to go left as far as possible. Then it reaches the end, so it'll output 1, pop back up, output 3. So you get 1, 3, and then you'll get up to 8. And the thing is, you've already output the left subtree, so it'll output 8. and then you'll go right, so you'll output 12, and then, I'm sorry, you won't do that. That's a preorder. You'll output, go left, 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 so you'll output 8.1, 9, 10, 12, and then 12 star. And here's how we know it's an inorder traversal, right? We know it's an inorder traversal because these elements are in order, and that's literally why it's called that. So here, are we going to output 17 first? No, because we need to output these 16s. So we go left, so we do 16, and then we go right, and we do 16 star, and then we pop back. We've already output this one, already done this one, haven't done 17, pop back, and now we're at 15, and we're done. Right? If 17 had a right child, all the right children would go here, right? Right children, whoa, right children, 17 would go in there. And you see here, it's absolutely impossible from this to tell what the order of the structure was. Well, I shouldn't say the order. What the structure of the tree was. Because I could have told you, I could say, oh, well, the root is actually 12, and 15 is the right child, and 8.1 is the left child. And you could build a whole bunch of different trees, right? Lots of different trees can be made from the inorder traversal. And the reason why is because the inorder traversal does something different, right? It basically just sorts everything from the data structure. So it's not actually giving you any information about the structure of the tree, unless, of course, as we do before, the exception is if you use parens, then you can recover the structure. And sometimes it's pretty useful to use parentheses and stuff like that, but yeah, so you can use parentheses to recover the actual structure. But if you don't have those parentheses, and it seems, at first it might seem a little bit counterintuitive, like, why do I need those parentheses? Why is it so important? But those parentheses are actually giving you almost more information than just the numbers are, right? So the numbers just sit inside of the nodes, but with the actual parentheses structure, so if you actually had something like this, where, let's see, what is the root? The root is 15. And then here we get this, and then I think something like this, right? Maybe 2 of them or something. That should only have 1 on it. That should have 2 on it, I think. Yes. And then here we're going to end up with, right, this, and then this, and then this, and then what else? So I think this, and then finally that. I think that's right. I could be wrong in terms of the absolute number of parentheses, because as you see, I was just doing that like in real time. So anyway, so you can actually recover the structure of the tree from this because you just look until you see something that doesn't have any parentheses around it, right? This has should have as many opens as closes. This should have as many opens as closes, so this one's the root. And then you look for the right child. So this one, you have to go in another set of parentheses, so you look for the one that doesn't have, that's just inside of one set, so that's 7. You look for the one that's just inside of one set. This is 1, 2, 3, 2, 1, 8, so that's the left child and that's the right child. So you can actually recover the data structure from those things. Otherwise, you cannot recover the data structure. But you see, that's not 100%. Like, if I ask you to do an inorder traversal of the data structure, the point of it is not to actually recover the data structure. The point is basically to sort the list of all the elements inside of the structure itself. So let's do a post-order traversal. Let's do that. So post-order traversal says go left, go right, and then output the node. So first we go left, then we go right, and then we output the node. So let's go left first. So we go left, 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 so we output 1. And then we go up, so we'll go output 3. And then we go this way, and before we output this 8, so don't output this 8, that would be an inorder traversal. We go right, so now we don't output this, don't output this, don't output this, don't output this, so we go 8.1, 9, 10, and then we don't output the 12, right, because that would be an inorder traversal. If we're at the 12 node, and we've just gone left to see 10, then we have to go right first, The next thing we have to do is to go right to C12 star before we see 12. And now that we've seen the 3 and we've seen the 12, right? So once you come out of there, this means that this is the right child of this node 8, so that means that there's nothing left to see, so now we see 8. And then we do the same thing on the other side. So remember that here we do this on this side, so now we go right. Right says go left. This says go right, so now we see 16 star, and we see 16 and 17. And then finally we see 15, because 15 is the root, so it comes last in the post-order traversal. Right, so this is, I will say that this is definitely, this shows up on every single test now. This is definitely a test question, because it's important that you be able to do this recursively. I've seen a lot of students who try to do this, for instance, like iteratively. So what they'll do is, I've seen some people do something horribly bad, and let's make it in the red color, so bad. Right, what they'll do for like a pre-order traversal is they'll do 15 and then, or I'm sorry, yeah, they'll do 15, and then they'll say 8 and 17 because those are the left and the right children, and then they'll do like 3 and 12, right, because those are the left and right children of 8, and then they'll do like 16, something like that, and then like 1, you know, etc. So, and you see why this is wrong. This is wrong because when you do this, it must be a recursive process, and so this is not a recursive process, right? So this is doing something very strange. If you're like jumping back and forth between nodes, there's no way that a recursive process can do that, because the recursion doesn't, like if you're at this node, if you pop out at one level, you go up here. If you push down one level, you either go here or here. You never go from this 3 to directly, well, I mean, you can do this, but you'll never go from this 3 to this 16 or for like any, you know, you don't go along any of these rows because there's no pointers along here. So there's no way to go from like 1 to this 9 or something like that, because you would have to know that you'd have to go up, up, right, left, left, right? And so that's definitely not what any of this is doing, right? It's just saying go left first, output, go right, or go left, go right, output. And so keep in mind that it always goes left first, then it goes right. So the only difference between pre, in, and post-order traversals are exactly that it goes in, you know, the only thing that matters is this thing, right? This thing is the thing that matters. So where you output the node value, that's where the value comes from. So next time we'll finish up with traversals. I'll talk a little bit about theory. We'll do a little bit about runtime, and then we will talk about AVL trees. So next time we'll talk about AVL trees, runtime issues. You know, by runtime I mean big O issues. And we'll finish up. We'll code up traversals. Which, I mean, I think at this point you can basically code them up because this is the code for it. This is like pseudocode for it. It's really not that complicated. You just put like a C out for the for output, and you would, I mean, these recursive calls can literally just be made. You might need a helper function that calls it on the root or something, but who cares, right? Okay, so that's it for this lecture. Yeah, I can put the code up. And, oh yeah, and then the next time we'll also try to talk about the project too. Okay. Yeah, let's put that code up on the GitHub. Let's go GitHub desktop, because I always forget to upload this stuff. All right, I'll handle it after class, but yes, I will. Now that I've loaded the program, I'll do it now. Okay, so that's it for today. Hopefully this made some sense. Maybe I'll try to fix up my deletion a little bit. I don't exactly love how complicated it was, but then again, I mean, it's not really the most trivial process. Anyway, so the point about deletion is that this is how to do it. Maybe next time what I'll do is I'll practice showing you more about how to actually delete, like if you're doing it visually, and maybe I'll put that on the homework just so that you get some practice not doing it with all the code, just thinking about the algorithm and doing it straight from the algorithm. Okay. Let us play the outro.